Welcome back to the TOC lecture. In the series of TOC lecture, we have already seen what is regular language, regular expressions, and we know that regular languages are recognized by some DFA or NFA. Now the question is, what if we apply some operation like set operation or other non-set operations? What is the outcome? What will be the outcome? That is, if we apply such operation, whether it will be in regular language or not. So such set operation we can say like union, intersection, complement, concatenation, and closure, and others than set operation like reversal, homomorphism, and quotient. So proving that union, intersection, union, concatenation, and closure are regular language, closed under regular language, closed under these operations is very simple. As we can see that if L1 equal to LR1, but R1 is obviously a regular expression and L2 R2, then we can easily say that union of L1 into it's also regular language, because we can write L1 union L2 equal to R1 plus R2, and we already know R1 plus R2 is a regular language. Okay, so this is very simple. And for L1 L2, the concatenation is also regular language, and closure is also obviously regular language, because for all these cases we can have a machine which is nothing but a DFA. The next thing that what if we apply complement operations on regular language, and whether it is in closed operation. So for that we said, for suppose let there is an DFA with machine variables like Q, set of states, this is the alphabet set, transition function, initial set, and then set of final state, and we assume that our regular language for machine for regular language for complement operation is Q, sigma same, tilde charm, start symbol same, but we can see there is a change Q, that is, it is a difference operation that is the set of all states excluding the final state. So how to prove that? That is, the complement operation is closed operation. So let's say there is a string, part of the alphabet closure. Now suppose we assume that W belongs to language of M. That is, if we start with initial state Q naught, we reach to one of the final states F. So if W doesn't belongs to LM, okay, if W does not belongs to LM, then it will end up in different state of M, different state of the DFA. So if If those states become final state, then uh, then in that case that W will be accepted. But scenario will be different because W was not in LM. Now taking further steps, W accepted by some machine, but we already constructed a machine using this operation. So you can definitely say that uh, W is accepted by W is accepted by a part of the language MCAP. So according to assumption, MCAP represent the complemented machine. So definitely we can see that the complement operation is also closed operation. So next we have to prove that whether the intersection operation is closed or not. That is, if there is do language, you have to see that intersection operation also closed operation. So start with to language L1 recognized by some machine M1, L2 recognized by some machine M2, whether M1 is something like that and M2 is this. Okay. Now the special attention should be paid here, that what is the structure of the states for the new machine. We have assumed that it is just a Cartesian product of the two set of states from the two machines. So it is nothing but a pair of states, the Qi, Qj, and the modified transition function should be like this: delta cap. Now this is a state for the modified machine, and this is the input symbol. So the output also a pair of states. Okay. In that case, we can also see that for Qk there is a transition function for the machine M1 like this, and transition delta 2 for machine M2. Okay. Now if I say for any string W, uh, it goes to one of the final state F cap if each of the machine M1 and M2, the W goes to final state of their respective set of final states. So we can see that W is also recognized by some machine, hence the intersection operation is also closed operation. Now this is some non-set operation, Jack reversal. We can easily explain with some example that reversal operation also closed operation. You can see this simple DFA, that a string of 0 1 1 recognized by this DFA 0. There are 4 states: Q2, Q0, Q0 to Q3, and Q3 is the final state and Q0 is initial state. This is initial state. The reverse is very simple operation. We have to reverse the edges of transition in reverse order. We change the final state to Q0 and The initial state is Q3 right now. So we can see that the string is reversed. String revert, it is 110. Previously it was 011. So we still have another DFA for reversal also. So it is recognized. We can say that it is recognized by some machine. So definitely it's going to say the reversal operation is also a closed operation. The next non-set operation is homomorphism. So let us first define what is homomorphism is. It is nothing but replacing the letter alphabets or symbols of the original language strings with the corresponding alphabets for the images. For example, for here you can see this is the W for the original string of the domain, and each of these symbols is replaced by this mapping function. This gives the image of the homomorph string. For all symbols replaced, and together these changed strings will constitute the language homomorphic image. It will be very clear from this example. Let's suppose this is the alphabet set AB, and it's a gamma for the homomorphic image, and each alphabet for the original language is replaced. A replaced by AB, B replaced by BBC. So if now this is W, we change each alphabets with the corresponding mapping, so that becomes your homomorphic image. So the new language should be LAA ABA. Sorry, this is the language, and the homomorphic image should be this. So it is clear from the example that homomorphic operation is nothing but replacing each alphabet of the string with the given mapping. And it is very easy to prove that the homomorphic operation is also a closed operation. So suppose in the example it is very clear that each alphabet is replaced by some substring. So we can see that these substrings are of fixed length, like AB, BBC, something like that. So for such fixed size substrings, we will definitely have DFA. For example, for AB we can have DFA like this, something like this, and it is true for all such fixed size substrings. So let's suppose we name this set of string as the languages. So L1, L2, LLN, LP, sorry. Now replacing the alphabets is nothing but concatenation of all these languages. So what I said, that for these all languages we have corresponding machines. So this machine actually is are the DFAs. Okay, so we can write this like concatenation of. Also we can say that L1 equal to LR1, something like that. So it is nothing but is equivalent to saying R1 R2 dot dot RP. So from the properties of regular expression, we already know this is representing a regular language. So homomorphism is also close to the regular operation. Next is very important operation called the right quotient operation, and it is defined like, suppose there is two language L1 and L2 with same alphabet sigma. So right quotient of L1 with L2 is defined as set of all string x, where strings of L1 is formed like x, y, and y also belongs to L2. So this is a formal definition. Let's come to the some simple examples here. L1, for example A, the L1 consists of these all strings, and L2 is 1 0. So you have to see that the first so A will be there is a matching, complete matching between these two. So A L1 right quotient will be 7 10 1 0 1 10 0 1 for A. For B, now you can see there is a no matching. If you try to do some format, it will nothing but, sorry, this is 5, this is 5, this is 5, so this is 5, this is also 5. Okay, because there is no matching for B. Now for the C, we see that for L1, first any numbers of ones, at least 1 1, then any number of zeros, then any number of ones. In the L2, that is at least 1 1. So we, in the both case, we have to see the ending ones and 1 in the L2. So there's a no there's a few strings where there will be exact match of number of ones at the end, and there are some strings where number of ones will be higher than L2. So in any case, there should be either no ones at the end or someone at the end. So we can represent this situation here like L1, L2. So first n and 0 will be there. We have to include 1p also, because with condition 1p, this condition will include all the situation like where there is an exact match, when there is a not exact match. So this is the final outcome for the right quotient. Proving that right quotient is closed under regular expression is also very easy. Suppose we have a machine for L1 equal to Ln, where m is equals theta q sigma delta q naught f. Okay, so now suppose we want to construct a machine m cap such that set of state will be same, alphabet will also be same, transition function q naught and state of modified final states, something like this. Now have to determine that for each state qy belongs to q, we have to determine that there exists a y belongs to L2 such that the extended delta function qi2 with y, it goes to one of the final state of L1. Okay, because we have to always find the common portion in L1, so we have to guarantee that y also belongs to L1. So you have to keep doing this okay. So if we do for each initial state qi, we can represent this also set of string as a language lmi, and I have to see if there is a intersection between L2 and lmi. If this happens, we modified our set of final state by inserting qi. So when you are done with that, we actually can say we're ready the construction for m cap. Okay, in this way you have to find the final states of m cap. The next thing we have to show that L m cap is equal to L right quotient L2. Okay, so that means that for our extended function we say that for q naught xy belongs to f according to definition. Okay, now we can break it down as delta star q naught x equals to q some state, and delta star qy goes to final. Okay, so by our construction we can say that by your construction construction we can say that q belongs to f cap and m cap accepts x because delta star q naught x is f cap. Similarly, in a converse, we can easily say that if x is accepted by if x belongs to L cap, then delta star q naught x equals to q belongs to f cap. Therefore, hence we can say that m cap is equal to, hence proved, that is homomorphic right quotient operation is also a closed operation. Thank you.